All right, let's take a look at our lesson for today. We're going to be working on fundamental theorem of calculus in a little bit of a different way than we had previously. If you recall, our first look at fundamental theorem was working with a definite integral. And after we integrated, it was like f of b minus f of a. Y'all remember that? That was our first look at it. This is a little bit of a different look at it to see how we can utilize this in other ways. So what I would like to do is work a problem two different ways. Method one is what we're accustomed to, where we would do an indefinite integral. So we're going to integrate this. And then, of course, we're going to have to do our plus c. And that's what we're used to. We have an initial condition. So let's proceed our normal way, the normal way that we would do it. So let's see, the antiderivative of 3x squared is x cubed. So I have y equals, the antiderivative of 4x is 2x squared. The antiderivative of negative 5 is negative 5x plus c. Then we would take our initial condition, we would plug that in, plug the 2 in, 5 times 2 plus c. Then we would do fantastic arithmetic, and we would figure out that c is going to be negative 7. So our particular solution, the one that has the initial condition of 2, negative 1, would be y equals x cubed plus 2x squared minus 5x minus 7. Then what they're asking us to do is they're asking us to find y of 3. So we take our equation and we're going to substitute a 3 in for the x. So I would have 3 cubed plus 2 times 3 squared minus 5 times 3 minus 7. Then after some, arithmetic, we get that that is 23. So our final answer, what they're wanting us to do is to find y of 3. Now y of 3 is 23. Now that's the way that we're accustomed to working these. What I would like to show you is the second way using the fundamental theorem, and it's highlighted right over here. It's the fundamental theorem. We're going to use that concept to work it a little bit of a different way. And this particular way that I'm showing you is especially helpful. So it's especially helpful with the calculators, using calculators like for, we've talked about it before, that it's not possible to integrate every single thing by hand, right? There are some integrands that we will not be able to find the antiderivative of, and that's why we have so many approximating techniques to use when we can't actually do it by hand. This is especially helpful. This technique I'm showing you is especially helpful with that kind. So probably the most common issue that students have with this is figuring out what numbers to put on the integral bounds, the lower and the upper bound. And so what I would like to kind of focus on, where we get the numbers from. So we get them from what we have. We have y of 2, so we have got to use a 2, and what we want. That's where the numbers come. They come from what we have and what we want. And we just put them in numerical order. We like to integrate forward. So I'm going to integrate from 2, because I have the 2, the y value at 2, and I'm going to integrate to 3 because that's the y value that I want. And so we are going to do that of 3x squared plus 4x minus 5 dx, and that's going to equal f. Actually, it's they're calling it a y, so right here is a y. So y of 3 minus y of 2. So that's the setup. What we'll do is we'll take this section right here and we'll find out what that value is, either by a calculator or by hand, whichever way we have available to us. And then we're solving for this one, so that one is going to stay a variable. And we know that y2 is negative 1, so we're simply going to fill in, negative 1 here. So I've got y 3 is what I'm looking for, and y2 is -1. So we're just going to plug that in. So we could put the left side in a calculator if we had a calculator. If we didn't, then we would just do fundamental theorem, just a regular old, we would take the antiderivative, which we already did up there, which was x cubed plus 2x squared minus 5x, and we would evaluate it from 2 to 3. And then we would do the fantastic arithmetic where we put all the 3's in, then subtract, put all the 2's in, and we get a number. Okay, I will tell you that that number is actually 24. If we put that in the calculator or we did it by hand, this number is going to be 24. So I have 24 equals y3 minus a minus 1. So we solve for y3, and y3 is going to actually equal 23, which is we've already done it. We knew that that would be the case. It checks with the one that we did previously. So I'm calling it method 2. It's just a different method to do what we have been doing. And in the next example, I think it'll become very apparent why this would be superior when we can't do the antiderivative by hand. So, for example, this very last one. We can't do the antiderivative of sine x squared. There isn't one that we can do by hand. We would have to use an approximation. Our calculators have a very robust approximation program that approximates integrals for us, ones that we can't do by hand, and even ones that we can do by hand. So let's set this up as a fundamental theorem problem, like method 2, and let's work through that. So how do I know what values to put on the bounds? I have what I want. I want f of 2. And what do I have? I have, where did they give it to us? So, I have f of 1 right here. So I'm going to go from 1 to 2 because, it happens to be from what I want to what I have. It's okay if they did the reverse. That's not a big thing. So we're going to integrate from 1 to 2 of sine of x squared dx. And that's going to equal f of 2 minus f of 1. Okay, so what I'm going to do is I'm going to pull up my calculator and we're going to input this left side of the equation in our calculator. I'm sure y'all probably already know how to do this, but I just want to make sure we're all good. So we'd go to a calculator page. We really, since we're integrating a trig function, we really want to make sure we're in radians, because if we're not, we're going to get the wrong answer. I'm just letting you know. It's going to be wrong. So please be sure you're in radians. Now, y'all probably have a faster way to do it than I do, but what I do is I do menu, and then I do calculus, and then I do integral. That's how I do integrals. And we said we're going to integrate from 1 to 2. And now I'm going to put in my trig function. So we've got sine of x squared. Close that out. Then this is with respect to x. And this is the value. This is the value that our calculator approximated for us on an integral that would be impossible to do by hand. So 0.494508. So let me go back to our document. And we have over here, so this is 0.494508. And f of 2 is what we want to know. We don't know that. We know that f of 1 is a -5. Okay, we do our algebra, we solve for f of 2, and we get that f of 2 is -4.505. So this is the really beneficial technique that we can use when we have to use a calculator to help us. So this question, if we'd been given f of 2 instead of f of 1, and we were asked to find f of 1, would that really be a big deal for us? No, not really, right? We would simply put in, I'm just going to put them, I would prefer to integrate forward. So I would put the 1 first and the 2 second anyway, but we would just, these would be reversed. And we would just solve. We would just use algebra to solve. So it's really not a problem. I don't want anyone to think that it's a big problem if we're given, instead of being given the bottom y value, we're given the top. It's not a problem. All right. So let's go to our second page and work some of these problems. We've got 2 problems to work. And so here what we're going to do is we're going to combine fundamental theorem with finding area under the curve, because that's really what an integration does, right? Is it finds the area under the curve. So here we go. This is telling us that this is f prime. So this is a graph of the derivative. That's f prime. And we have to be given an initial condition. I'm just going to say, we can't fly blind. We have to have an initial condition. If we don't, we're going to have to put plus c on everything, which really isn't that handy. So typically they're going to give you an initial condition. Ours says that the position at -2 is 0. I mean, it could be anything, but they're telling us it's 0. So that's what we have to go by. So we're going to set up our fundamental theorem, because we need to find the function values. All of these points on this graph are first derivative y values, right? These are first derivative y values. We want function values. In order to get that, we're going to have to do an integral. So we're going to go from the x that we know, which is -2, to the x that we want, which is 0. And I want to, again, integrate forward. I want to be going integrating forward, because when I integrate forward, the area above the x-axis has a positive sign and the area below the x-axis has a negative sign. If I were to integrate backwards from big X to little x, then that would all reverse, and that is really confusing. So when we're doing an abstract problem like this, I would recommend that you integrate forward. Okay, so here we go. We're going to integrate forward f prime of x dx, and that's going to give us f of 0 minus f of -2. Now, I know you probably already know this, but I'm going to tell you that some of my students that like to conserve energy, they really don't want to write this part, when in fact this is the most important part that you're going to write. This is the most important part. That is like your work. If you don't write that and you just write down some, arithmetic, that is not going to cut it. Okay, so you have to write down the integral. You have to write down the integral. So I hope that that's clear enough. We're writing down the integral. So I'm going to go over here to my graph, and I'm going to calculate the area from -2 to 0. So we're going to be looking at this area in here, -2 to 0. It's a triangle. Half base times height. So that is going to be, 4. So this is 4 equals, f of 0 is what we're looking for, and f of -2 is what we were given, and it's 0. So we know from our work that f of 0 is 4. All right, how are we doing? Now, to find f of 2, I can start at -2 if I want. I can start at my original point, but I feel pretty confident about the new point that I wrote. I'm feeling pretty good about this. So I am actually going to start at 0. I'm going to integrate from 0 to 2 instead of -2 to 2. You can do it either way. Doesn't matter. You're going to get the same answer. But again, I'm feeling pretty good about this. So I'm going to utilize this information in my new integral. So we're going to integrate from 0 to 2 of f prime of x dx. And that's going to be f of 2 minus f of 0. So we go back over here to the graph. We're going to accumulate the area between 0 and 2, the part that I did in green, which is it's the same as the yellow portion. It's equivalent, so it's 4. And then f of 2 is what we're looking for. And f of 0 we found was 4. So doing our algebra, solving for f of 2, I get 8. Okay, so now I know that f of 2 is 8. Okay, we getting the hang of it? Everybody okay? All right, so the last one, again, I'm feeling pretty good about this answer right here. F of 2 is 8, so I'm going to integrate from 2 to 6. That's what I'm going to do. Again, that's just a choice that I'm making. So I'm going to integrate from 2 to 6 of f prime of x dx. And that's going to give me f of 6 minus f of 2. So we go over here to our graph. We're going to go from 2 to 6. That's this part right here. Since we're integrating forward, that has a negative. That area has a negative sign. So we know that's what, a half a circle. So half pi r is what, 2 half pi r squared. So that area is what, negative 2 pi equals f of 6 minus 8. So finishing this out, I get f of 6 is 8 minus 2 pi. And that's using the fundamental theorem in conjunction with a graph of the first derivative. Okay, how are we doing? All right, the last problem, we're going to do something similar. The only issue here is they already indicated the area. Now that's quite interesting. All of these numbers are positive because they're just indicating the value of the area under the curve. They're not attaching a sign to it. They don't know whether you're going to integrate forward or backward, so they're not going to put a sign on it. All right, you are going to have to put a sign on it. And again, I would recommend that you integrate forward. So here we go. What we have is f of 3. That's what we have. What we want is f of 0. So I'm going to integrate from 0 to 3 of f prime of x dx. And that is f of 3 minus f of 0. So this part right here is the most important part you're going to write. Please, like internalize that. That's the most important part, the integral part. And now we're going to do our calculations. So 0 to 3 is this bit of area in here. We're told that that's 4. So 4 equals f of 3 we know is 5 minus f of 0. So we solve for f of 0 and we get 1. So f of 0 is 1. Okay, now let's work on f of 7. Okay, f of 7, so that's a 3. I think I would like to go from 3 to 7 because I have 3, it's right here. And you know, that I think that's cleaner. That's what I would like to do. So I'm going to integrate from 3 to 7 of f prime of x dx. That gives me f of 7 minus f of 3. So the area they told us is 9. We're integrating forward, so that's a negative 9. F of 7 we don't know. And f of 3 is 5. So doing our lovely algebra / arithmetic, we get f of 7 is negative 4. Last one, f of 9. I think I would like to integrate from 7 to 9 because I have f of 7 already and I want f of 9. That just gives me this last part over here. That seems kind of handy just to integrate that last piece. So we're doing f prime of x dx equals f of 9 minus f of 7. So that area is 2. F of 9 we don't know. F of 7 is a negative 4. So f of 9 is actually negative 2. Okay, they want us to sketch the graph of f. Look at all those position values we have. That's kind of nice. Let's just plot the position values. So 0, 1. We know 3, 5. That was our initial condition. So 3, 5. Let's see what else we know. We know 7, negative 4. Okay, and we also know 9, negative 2. Now, I would just like to connect all the dots, but I want to verify that I'm doing this correctly. So I'm going to do a little sign chart over here for this derivative, just to make sure. So we're above the x-axis, the derivative is positive, below is negative, above is positive. So what that's telling me is from 0 to 3 I'm increasing. Yeah, that seems good. From 3 to 7 I'm decreasing. Okay, I agree with that. And then from 7 to 9 I'm increasing. So great. I mean, it would have worked out fine if I had just, graphed it like that, but I wanted to verify with the sign chart on. This is f prime. All right.